Abhishek Agarwal on strongly coupled 2+1D Yang mills.
Thank you so much. So we're going to be talking about some work that we're doing in collaboration with Abhishek Agarwal and Vinaya. And what we're trying to do is get a handle on the strong coupling dynamics of Yang mill series in three dimensions. So in this talk, I'll start with a brief review of the formalism developed by Agarwal and Nair, or the KK formalism. So in a very impressive series of papers, started in the mid-90s and considering the 2000 or so, KKN worked out a gauge invariant Hamiltonian formalism for analyzing Yang mill series in three dimensions. And they analyzed just pure Yang mills on R3 with great detail in the series of papers, and they were able to come up with a very impressive set of results, for example, the computation of spring tension and so on. I'll talk about some of the results as I go along. So because we have these techniques available to us, it's important to thank you to push this formalism and see if we can do a little bit more. There are of course many open problems that we would like to understand for gauge series in three dimensions. In particular, what we did recently was figure out how to add matter fields to Yang mill series in three dimensions and do a Hamiltonian analysis for this coupled system in a manifestly gauge invariant language. And we sort of set up the formalism and also calculated, for example, things like the potential energy between matter sources in the three-dimensional theory. So I'll try and describe this setup and these calculations for you in some detail. And the other avenue in which we are trying to push the KKN formalism has to do with analyzing Yang mill series, three-dimensional Yang mill series on spaces where the spatial geometry, the spatial part has, the spatial geometry is a compact manifold. So we take the particular example of R cross S2 as a prototypical example, and there are various motivations for doing that, which I'll talk about as I go along. So I mean, I don't need to remind anyone here that studying gauge theories at strong coupling is an extremely hard problem, and that is one of the leading motivations that, for example, prompts us to look at the ADS-CFT conjecture in as much detail as we do. So gauge theories in general at strong coupling are hard, but there is a small window of opportunities if we look at gauge theories in three dimensions. So Yang mill series in three dimensions, unlike their two-dimensional cousins, have non-trivial propagating degrees of freedom. They have the nice features that we typically associate with gauge theories: asymptotic freedom, confinement, non-perturbative mass gap in the spectrum, etc. Although, although they have these nice properties, they are simpler than their four-dimensional cousins in the sense that they tend to be super renormalizable. Their coupling constant, the coupling constants of these theories tends to be dimension full. And it turns out that due to this work of KKN, there are a nice set of mathematical techniques also available to us to tackle gauge theories in three dimensions and make the most of this little window of opportunity. So for example, in their work, KKN were able to compute the non-perturbative mass gap of pure Yang mills theory on R3, and it is given by this simple formula. It's just the 2th coupling divided by 2 pi. And this number can actually be checked from independent calculations. So for example, glue ball masses in three dimensions have been computed on lattice by lattice simulations for a long time. And the non-perturbative mass gap of the three-dimensional theory sets the overall scale for the glue ball masses. So it can be factored out from the lattice calculations and compared with the analytical results. And it does match up very well. There is also a very direct physical, I mean, this number is also very relevant in an actual physical context. And that has to do with four-dimensional Yang mill theories at high temperatures. As we know, the non-perturbative mass gap of three-dimensional QCD is related by the usual arguments of dimensional reduction at high temperatures. It's related to the magnetic mass of the four-dimensional theory at high temperatures. And of course, using various resummation techniques and so on, there are various estimates of the magnetic mass at the high temperature in the high temperature phase of QCD, and this number can be compared with those estimates also, and it does match up very well. And KKN were also able to compute, for example, more impressively, I guess, Wilson loop expectation values and give a very simple formula for the string tension in 3 dimensions. So for a Wilson loop in representation R, the string tension in their calculation is simply given by this formula, where C sub A is the Casimir in the adjoint representation. And of course, this number has also been computed with great care by lattice gauge theorists over an extended period of time. For example, in particular, Mike Tepper and his collaborators at Oxford have been calculating the string tension in 3 dimensions for various gauge groups in 3 dimensions, SUN gauge theories for various values of n, various representations, etc., for a long period of time now, and they have a very good grip on very good control over the errors that creep into the lattice measurements. And if we compare this formula to the latest estimates that come about from Tepper and his collaborators' work, then it is within less than 1%. So what I would just like to emphasize by these sort of little advertisements is that there exists this formalism, which I'll describe in some detail now, but it's not just a pretty formalism, it is actually useful for concrete calculations, and these things are, for example, some of the results that one can obtain. However, this cannot be a complete story. So for example, this result to the was computed by KKN up to a certain order by computing the vacuum wave functional to up to a particular order, and this is supposed to be valid for all representations, and we know that all representations do not confine. For example, there should be screening effects in the 3-dimensional theory, which were not seen by KKN to the order that they calculated. So for example, just within this little setup of 3-dimensional Yang-Mills theories, there are things to be understood. And of course, we would like to extend the formalism in various different ways. So, like I pointed out, if we had, for example, quarks in the adjoint representation, we should not get confinement. We should get screening for heavy adjoint sources. And this wasn't seen to the order to which KKN computed the vacuum wave functional of the theory. And this, on the face of it, is a bit of an unsettling aspect to what they did, and we would like to improve upon that. So there are many ways that one can try and see screening effects. One kind of direct way is to just add matter fields to the formalism, which would require us to understand how matter fields can be coupled to Yang-Mills theories in 3 dimensions in a gauge invariant way, and then try and analyze this larger system. And that is basically what we did. And in the process, we figured out how to couple matter fields covariantly to Yang-Mills theories in a gauge invariant language. What I'd like to point out is that there are at least 2 other good reasons for doing this exercise. So as I alluded a second ago, if one looks at pure Yang-Mills theories in 4 dimensions at high temperatures, then due to the usual arguments of dimensional reductions, only the 0 mode of the A0 component of the 4-dimensional gauge field survives, and it essentially acts as a sort of adjoint matter field. And essentially, the dynamical system that one has to analyze to get a grip on 4-dimensional Yang-Mills theory at high temperature is the 3-dimensional gauge theory coupled to adjoint matter fields. Of course, there are all kinds of complicated corrections which are incredibly hard to compute, but one can get a fairly good idea for the potential for the adjoint field using resummation techniques and so on. So this is at least one physical context to which we would like to apply our formalism to. And of course, the other motivation, which is very close to my heart, has to do with supersymmetrizing the formalism, which also boils down to figuring out how to add matter fields to the 3-dimensional gauge theory in a gauge invariant language. And of course, supersymmetric gauge theories in 3 dimensions are extremely interesting. There's this whole body of work due to Seiberg and Witten, and where they tell us what the strong coupling behavior of these theories should be like, and we would like to at least test some of those conjectures directly from first principles. And in particular, one problem that we are interested in and working on has to do with understanding gauge gravity duality in 3 dimensions. So recently, and by recently I mean a couple of years ago, for example, Lin and Maldacena came up with a concrete proposal for the string dual for 3-dimensional Yang-Mills theory with 16 supercharges. So the gauge theory in question is basically just a dimensional reduction of n equals 4 super Yang-Mills from R cross S3 to R cross S2. And they computed, using worldsheet techniques, the leading order corrections to the energies of operators formed out of scalars, and they have sort of very non-trivial predictions for what the strong coupling spectrum of the gauge theory should look like. And we would like to test that. I mean, the usual apology that we always have to come up with while not being able to test the gauge gravity duality in as much detail as we would like to is that strongly coupled gauge theories are hard. But here, at least, sort of motivated by the success in understanding strongly coupled pure Yang-Mills theories and in 3 dimensions, there's at least the hope that we might be able to do a little bit more and maybe come up with some concrete tests of the gauge gravity duality in 3 dimensions. Anyway, so there are all these motivations, but a lot remains to be done. So let me now start with a brief review of the KKN framework. So we are in 3 dimensions, and we have a pure Yang-Mills theory. So we start with the A naught equal to 0 gauge. We have 2 components of the gauge fields remaining. Let's make complex combinations, call them A and A bar. And the key idea that goes behind the KKN formalism is that instead of thinking about A and A bar, one can parameterize these complex gauge fields in terms of a complex matrix M and its adjoint. So M is SLNC valued. So del is just the operator del, the derivative with respect to the z direction, z being x plus iy. So the advantage of this parameterization is that gauge transformations, local gauge transformations on A, simply show up as left multiplications of the complex matrix M. So of course, by construction, this matrix H, which is M dagger M, is gauge invariant. Now, there are a couple of caveats that we have to keep in mind. This is a good parameterization because it can be inverted, and M can be expressed, at least formally, as a power series in the gauge potentials. And it can be inverted because the Dirac operator for massless fermions on the plane doesn't have 0 modes. So this is really a one-to-one correspondence. Not quite. We have to, though, keep in mind that if I multiply M by a matrix V bar, which depends only on the antiholomorphic coordinate, then it gives me the same gauge potential. So what we have is a sort of new holomorphic invariance in the theory. In fact, what we have done is trade one symmetry, that is gauge invariance, for another symmetry, which is holomorphic invariance. It just turns out that this is much simpler to incorporate in the gauge theory, and in fact, it's a very useful symmetry that tells us how to, for example, regulate the theory while doing computations. So modulo the holomorphic invariance, we basically have identified a set of natural gauge invariant variables. But of course, this change of variables is a non-trivial one, and it comes with a non-trivial Jacobian. So if I just look at the measures on the space of gauge potentials and compare that to the measures on the space, the measure on the space of these Hermitian matrices H, then the two are related by determinant d bar d, but this is the covariant massless Dirac operator. But this can be computed. It's just a 2-dimensional anomaly calculation, and it is given by just the Wess-Zumino-Witten model for the Hermitian matrix H. So the measure can be computed, and here it is. And we have to keep in mind that anytime we compute any norm or overlap or things like that, we have to do so with respect to this measure on the space of the matrices H. And of course, if we analyze, for example, self-adjointness issues, then also we have to put the measure factor in all our considerations. So we have 2 of the 3 ingredients that we need for our formalism. We have identified the Hilbert space, that is the space of that's the space of functionals built out of the matrix H, and and we have the norm on the Hilbert space. I should also point out briefly that because the sort of measure factor has this Westermino-Witten contribution, it also tells us that instead of H, we should be using the current of the Westermino model, del H H inverse, as the natural dynamical variable. Of course, because H is gauge invariant, so is J. So now comes the difficult part, which is the rewriting of the Hamiltonian itself in terms of the currents, J's. So we start with the usual description of the Hamiltonian. Let's look at the kinetic energy term, which is basically the Laplacian of the space of gauge potentials. At a formal level, at least, all one does is to apply the chain rule of derivatives to write this instead of in terms of functional derivatives involving the current. But this is just a cartoon for what we really do, because if, for example, if one were to take this literally, then all these expressions would turn out to be highly singular. They would typically involve the Green's functions of the massless Dirac operator in 2 dimensions at coincident points. So they need to be regularized, and that is where the subject becomes highly technical. And I won't go into the detail, but just to give you a flavor of how it is done, what we do is basically carry out the regularization by splitting points. But of course, one can split points in many different ways. But one guiding principle that we use is that, and indeed, I should point out that if one tried all kinds of point splitting prescriptions, one can even show that one will get nonsensical results depending on how one split the points. But if one uses the guiding principle of holomorphic invariance, that is, if one regulated the theory by splitting points in such a way that the holomorphic invariance is preserved at every step of the calculation, then one does get a unique answer. And that is indeed what we do, what KKN did. And the expression for the kinetic energy term, for example, expressed in terms of the currents, looks like this. Again, one has to, anyway, so it has 2 terms. The first one is a harmonic oscillator term, which immediately gives us the non-perturbative mass gap in the theory, which is m, the 2th coupling divided by 2 pi. And then there's an interaction term, I call it omega here. Omega is nothing but, but a sort of covariant derivative acting on the Green's function of the Dirac operator. And in this covariant derivative, basically, J is playing the role of the gauge potential. So it's a non-local Hamiltonian, and it is manifestly gauge invariant. And although it's not obvious, one can even show that it is holomorphic invariance, and it's also self-adjoint. Although it doesn't look so, but remember, the self-adjointness issue has to be analyzed with the proper measure factor put in place. So we have rewritten the kinetic energy term in terms of the J's. One can also rewrite the potential energy term quite easily in terms of the J's. Basically, B becomes del bar J. And the potential energy term goes as 1 over m, while the kinetic energy term goes as m. So in the regime where m approaches infinity, the strongly coupled phase, this infinite coupling regime, the Hamiltonian, the kinetic energy term dominates and can be thought of as the strong coupling Hamiltonian, at least the starting point.
I mean, coupling constants dimensional, right?
Right.
The mass gap is of the same order as the coupling constant.
Right.
So in what sense is there a meaningful limit in which E squared n goes to infinity?
Well, let me come to the expression for the vacuum wave function. I'll talk about it in a second. So I mean, for now, we just think of it as a parameter, and we will give a sort of meaningful definition to it in a second. What I would like to, I mean, basically to answer your question, it is kind of interesting to go to the calculation of the vacuum wave functional a la KKN. And the way it was done was the following. So let's try and construct eigenstates of the kinetic energy operator. The simplest eigenstate, non-trivial eigenstate, is given by functionals that have a single J field with eigenvalue m. Now it turns out that these are normalizable eigenstates because, remember, our measure has the Westermino-Witten factor. What is not so obvious, but is indeed true upon calculations, is that the potential energy is also an exact eigenstate of the kinetic energy term with an eigenvalue twice m. Now, we can try and use this last equation to start an expansion in 1 over m for the determination of the vacuum wave functional. It really is an expansion in k over m, but anyway, so this is really what we do. So to do the vacuum, to compute the vacuum wave functional, we first notice that the C number, I get the C number wave functionals, just the number 1, for example, is a perfectly admissible zero energy normalizable eigenstate of the kinetic energy operator. It's normalizable once again because of the Westermino-Witten factor in the measure. So this is, in the extreme strong coupling regime, an exact eigenstate of the Hamiltonian. But we'd like to do a bit better than that and take into account the effect of the potential energy. So what we do then is to improve upon that, and this is what KKN did, is to come up with an ansatz like this for the vacuum wave functional, where P is a functional involving the J's to be determined, and it can be determined in an expansion in 1 over the mass gap. So to leading order, for example, P is just quadratic in P is proportional to the potential energy term, and this is indeed so basically the action of T on P has to cancel out the action of the potential energy term on this, and that is possible because the potential energy term is an exact eigenstate of the kinetic energy term. And then there are all kinds of other corrections, which can in principle be computed. So if one were to, for example, sum up all the pieces that are quadratic in del bar J, and this was done by KKN, one will get the Gaussian bit of the vacuum wave functional is given by a functional like this with a non-trivial kernel K given by this. So now to come to your question, how do we interpret this kernel? So what do we indeed mean by strong or weak coupling in this framework? So if we think of if we are interested in the vacuum wave functional for the theory for all momentum modes greater than this number set by the mass gap m, then indeed the vacuum wave functional, when it is expanded in this in k over m to leading order, is just given by this, which agrees with perturbation theory. But strong coupling really means looking for the vacuum wave function of the theory for all momentum modes less than this number m, and that so if we expand out the kernel in k over m, the leading order piece is indeed given by this. So this is really how we interpret strong coupling in this dimensionful theory.
I'm confused. That doesn't look Lorentz invariant.
Which one?
Well, the kernel that you had in there.
Right.
That's the spatial kernel, right?
Right.
So the expression doesn't really look Lorentz invariant any longer. Well, you have this wave functional, and it doesn't look particularly gauge invariant because.
No, it is gauge invariant because J is.
Sorry, Lorentz invariant.
Right. So the dispersion relation is Lorentz invariant. We get a collection of J particles which are described by this current J, which have a mass m and have a dispersion relation given by this.
What I don't understand is why the different K modes have different. Basically, I wasn't expecting momentum dependence on the vacuum wave function because it's not particles.
No, I mean there would be a momentum dependence of the vacuum wave functional, right? Why is that not to be expected?
I would expect that it would be uniform in K. All modes are the same because they can be transformed by Lorentz transformation.
Oh, right. So, yeah, I mean,
I know you've broken Lorentz invariance when you define J's, but it really looks very non-Lorentz invariant.
Right. No, it is though. I mean, in the sense that one can verify, for example, the Poincare algebra and so on. So it is Lorentz invariant, but it's probably realized in a very strange manner.
Okay.
But we do get a theory of basically massive particles. So, for example,
Is
if
it
we
supposed to be real?
sorry,
Is P meant to be real or is it complex?
P the vacuum wave. Yeah, this is. I mean, this is sort of just a probability distribution, right?
You've got deep bar derivatives, but
Right.
aren't they complex?
Well, there's, I mean, this is just nothing but trace of b squared, for example. So I mean, at the end of the day, we are just dealing with real quantities. It's just that we use the complex notation to simplify our calculations.
Yeah, but why are you choosing d bar rather than d there? Is there some?
This one?
Yeah.
It's just a choice of polarizations. We had the dynamical variables in the theory. We had J, we had J bar, etc. Now, at some point, we decided to choose make a choice in terms of polarizations, just like we choose Q instead of P in a quantum mechanical calculation. So one could just do the calculation in terms of another polarization, for example. It would just be.
You don't have to add the two together, really.
Sorry?
I thought there was a symmetry between d and d bar when you started off, and that symmetry has been somehow broken.
Well, we did make a choice at some point. There were the fields M and M bar. Now, the Westermino-Witten model has two currents, and we decided to work in terms of one.
Right.
So it's just a reflection of that choice. So in this sort of K over M expansion, like I said, I mean, the vacuum wave functional is given by just this simple, completely local object to leading order. But of course, there are all kinds of corrections, which in principle at least can be computed. But the nice thing about this is that this is nothing but the action functional, if you like, of a 2D Euclidean Yang-Mills theory. So if one were, for example, to compute the vacuum expectation value of a purely spatial quantity, like a spatial Wilson loop, then that is just a path integral computation in the two-dimensional setup with of a 2D Wilson loop with a 2D Yang-Mills action. And that, of course, has been studied in great detail. It's just that the coupling constant of the two-dimensional theory, which is proportional to the coupling constant of the three-dimensional, proportional to the square of the coupling constant of the three-dimensional theory, is determined by an actual three-dimensional calculation. So the constant of proportionality is fixed by the calculation of the wave functional. So once that is fed in, one can just take the results from the two-dimensional Yang-Mills theory computations and write down a formula for the string tension, which KKN did. And this is the...
To the wave function, corrections to that formula.
Absolutely. Absolutely. In principle, they should give corrections of order 1, but for reasons that we don't understand, they don't. They give corrections of almost order 0. And it is really something that it works well than it has any right to. So as you pointed out, I mean, in principle, if I were to calculate the corrections, I should get all kinds of corrections to this formula. But this formula itself, just starting from the leading order vacuum wave functional, is within less than 1% of the lattice data. So maybe there's a hidden parameter in the problem which we just haven't seen because of the way we have written things out.
Is the calculation valid mostly at large N?
In the way KKN originally did the calculation, large N doesn't enter the picture at all. But it is true that agreement with lattice data increases with increasing values of N. But you could do a heuristic analysis and see if the higher corrections are lower order somehow in 1 over N. And that's not so. So the obvious thing that comes to mind, 1 over N, is really not what is making the correction small. There is something else. So, but I mean, so it's nice that the number agrees with the lattice results, but of course it cannot be the full story because this 2D Yang-Mills theory confines in any representation, and we don't want that in the three-dimensional setup. So the corrections, for example, to the wave functional, if we did compute them, maybe they would somehow give small corrections to the string tension, but they would give rise to screening effects. And this is the kind of thing that we wanted to see, and that basically led us to do what I'll be talking about next. So essentially what I'd like to point out is that that KKN have this Hamiltonian formalism that does allow us to do some calculations, for non-perturbative calculations for three-dimensional Yang-Mills theories. But of course, there's a lot to be done. And we don't know how, I mean, So the screening effects were not very clear, as it turns out in their setup. How to extend the setup to include supersymmetry or to include non-trivial spatial geometries, etc. All those were kind of open issues which we are trying to analyze one by one. So let me now talk about screening effects and how to add matter fields into that formalism. So heuristically, what we would expect to happen is the following. So for example, if we threw in heavy adjoint matter fields, scalar matter fields, well, let's call this phi. The phi is a scalar field. And if we looked at a heavy scalar fields bound together by an adjoint Wilson loop, then the picture that we would expect is the following, that the Wilson loop will stretch out up to a particular distance, and then at some point it's going to become energetically favorable for these bound states to form, bound states of phi with, for example, the B field. These are called the glue lump states in lattice literature. And when it does become energetically favorable, because then the Wilson loop will split up. So there's got to be a finite overlap between the unbroken Wilson line and the glue lump states. And this phenomenon of adjoint string breaking, which can occur for other representations of zero anality also, has been studied on the lattice. So the one simulation that we looked at was done by Forkrand and collaborators, where they simulated the potential between heavy adjoint sources on the lattice. So this is a cartoon of the actual simulation that they did. They see that the potential grows linearly. There's a confining potential between the adjoint quarks or scalars. And then at some point, the potential becomes independent of the distance between them, and that's basically a signal of these glue lump states forming. And if we translate the results of Forkrand et al. Into our units, then the string snaps at this value in terms of, in the scale of, in units of the non-perturbative mass gap. So what we would like to do is basically see effects like this, which are not seen at all if one just naively use the formula for vacuum wave functional a la kkn. So there are many ways one could try and see this, as was alluded to. One could try and compute the corrections to the vacuum wave functional and just derive this screening property, purely within a pure Yang-Mills setup, which is substantially more complicated than what we did. One could try and compute this overlap, which is 1 over n, which is a 1 over n effect, also within the pure Yang-Mills, within the setup of the gauge theory coupled to matter fields. That is also, and that overlap is indeed what the lattice gauge theorists calculate. We don't do either one of the two. What we are going to do is basically throw in matter fields explicitly by hand, write everything in terms of gauge invariant variables, and compute the binding energy of these guys and identify twice that binding energy with the string breaking energy. That is sort of the simplest thing to do, and also it sort of allows us to figure out how to add matter fields, which we want to do for independent reasons anyway. So this is the problem that we did worked on recently. So we start with, again, just Yang-Mills theory coupled to matter fields, just a single adjoint scalar now. Once again, in terms of, we replace A by the complex matrix M. So H, which is M dagger M, is once again gauge invariant. And indeed, what we would like to do is replace A by the current of the Westerwiener model J. Of course, phi transforms in the adjoint. So if I conjugate phi by M dagger and M dagger inverse on the left and right, then I get a new field upsilon, which is gauge invariant by definition. So once again, I go through the machinery, use basically at a formal level the chain rule of derivatives. Think of A and A bar as depending on J and upsilon. Actually, only A bar depends on upsilon because it involves M dagger. And do this and rewrite everything after regularizing the theory carefully, using holomorphic invariance as a guiding principle. So the kinetic energy term is kind of trivial to write down. It's just the naive kinetic energy term for the upsilon fields, as one would expect. Let's look at the d bar phi d phi term. That, when written down in terms of the upsilon fields, takes on an interesting form. D bar basically just becomes the ordinary derivative del bar, and D gets replaced by a holomorphic covariant derivative where the role of the gauge potential is played by J. What is interesting to see is that there is no quartic coupling between the gauge fields and phi's anymore. It's just cubic. Trace B square, once again, it's just del bar J. The kinetic energy term is once again the most involved, it presents us with the most challenging calculation because of all these regularization issues. But nevertheless, one can write it out explicitly as a functional differential operator involving the J's and the upsilon fields. And this is the final result. So the Hamiltonian is just the Yang-Mills split, has the Yang-Mills split, which we had previously in the pure Yang-Mills, in the study of the pure Yang-Mills theory. Then we have the kinetic energy term, the mass term, and the new cubic coupling, if you like, between the covariant coupling between the upsilon and the J fields. But the kinetic energy term also picks up a piece, which is a cubic coupling, which is once again non-local, but nevertheless goes as M. So if we were to repeat the story of doing a calculation in an expansion in 1 over M, then this would really be a dominant piece. So once again, this Hamiltonian is self-adjoint, and it does have holomorphic invariance, and it can and it is manifestly gauge invariant. Adding more matter fields is trivially carried out. So for example, if it can be trivially extended to the case of multiple scalars, and there is also a parallel formalism that allows one to introduce fermions, which can basically allow us to write down gauge invariant versions of supersymmetric theories. But for now, let's just look at this guy that we have. So we have the Hamiltonian, which has the usual properties of holomorphic invariance, etc., that we would expect. But what we would really like to do is to use it to do an actual computation, the computation of the binding energies between these glue lump states. Of course, what aids that computation is that in the large little m, large capital M limit, we know what the vacuum wave functional is. It's just the product of the Yang-Mills wave functional that KKN computed times the oscillator wave functional. And let's work within this large mass limit, sort of it'll give us a quenched approximation to work in. So what we now do is to generate excitations, or rather position space representations of excitations around this vacuum. And these excitations we want to be the glue lump state. So we take a local operator like this. What we really do is to sort of smear it out with a test function f, and write in terms of gauge invariant variables. And this Wilson loop that we insert a Wilson line between them, and we have the del bar J and the upsilon fields, and then some sort of a test function. And we want to act on it with the Hamiltonian and compute its energy. So for example, if the operator is...
Just a naive question. In the previous calculation, you had the potential energy term, you had TV being 2mv or something.
Right.
You had this eigenstate relation.
Right.
And I thought that was important. Do you have anything like that in the previous?
No, absolutely. That is very important here, because that goes into the calculation of this bit of the ket 0. So once that's, that is absolutely, I mean, the knowledge of the leading order behavior of the strong coupling vacuum wave functional involves that calculation. And once we have this, and once we have this non-trivial measure on the space of wave functionals of J, we can just construct position space representations and try and figure out their eigenvalues like we do for the harmonic oscillator in quantum mechanics. This is really a sort of prototypical quantum mechanical exercise, if you like. So we have this mirrored out glue lump state. We act on it with H. And what we see is that in the regime that this function is sharply peaked around some value of the separation x minus y, call it lambda, the action of H on the glue lump state can be translated into a Schrodinger equation for the function f. And the Schrodinger equation involves the Coulomb potential, as we would expect. So what we do is basically get the right Coulomb behavior in the regime in which the glue lump state is is a truly local object, which would be which is sort of the short range approximation, if you like. So basically, if we ignore the kinetic energy term, which if we think of both little m and m as in the regime that they go to infinity, what we see is that these local Glulam states become exact eigenstates of the Hamiltonian with this eigenvalue. So there's the mass of the scalar, there's a little contribution from the mass gap of the, so it's just the mass of this guy plus the mass of this guy plus a little logarithmic correction that comes from the Coulomb term. So in the extreme strong coupling regime, this twice the binding energy, that is twice m, can be thought of as a lower bound for the string breaking energy, and that is indeed consistent. But as the lattice data suggests, the Glulam state really does stretch out to quite an extent before snapping. So we should really be thinking about computing the binding energy beyond the extreme strong coupling regime, where there is some kinetic energy term between where the string really does stretch out. So this is, and that is of course a substantially more difficult problem, and this is what we were trying to analyze. So once again, we look at the Glulam state, which is now where f is now no longer forced to be sharply peaked around a particular value of the separation. And once again, this is sort of a position space, space representation of an excitation around the vacuum wave functional that we have a handle on. If we take another state like this and compute the overlap, it turns out that we can translate the computation of the overlap into a Schrodinger equation once again for f within a quenched approximation. Basically, this calculation is sort of like the standard textbook exercise that we are all familiar with that relates the area law behavior to the linear potential between quarks in QCD. Except, instead of interpreting the area law and deriving the potential, what we start with is the vacuum wave functional, which does give us the area law confinement, and then basically reverse engineer to read off the potential energy between these fields. And we can actually do this calculation from first principles within a quenched approximation, and this is the sort of Schrodinger equation that we get, and it does have the expected linear behavior. It will have also the Coulomb part, the logarithmic term, but that is subdominant in the analysis. So then, of course, the task becomes basically it reduces to solving the Schrodinger equation and figuring out the binding energies of the two-dimensional Schrodinger equation with a linear potential. And we did that numerically, and we computed the number, and the binding energy, the string breaking energy from the analytical calculations that we did comes out to be this number. And if we compare it to the lattice estimates, it's within 9%. So at the end of the day, once we go through this whole machinery, at the end of the day, we can calculate a particular number and compare it with sort of quote-unquote lattice experimental data. After talking to some of the people who were involved in this lattice calculation, they tell us that they are themselves not very happy with the errors that they had in their computation. So we believe that the agreement would actually be significantly better once a better sort of lattice estimate is found. So just as a consistency check, we can also go through this argument and compute the mass of the lightest glue ball and compare with lattice results. And then our results are a little more off, but that is to be expected because we are working in a non-relativistic regime, which is not really justified when one looks at the glue ball masses. One doesn't have this extra parameter, capital M, to control the calculations. So what I would like to say is basically at this point we have figured out how to add matter fields to three-dimensional Yang-Mills theories and write down a gauge invariant form of the Hamiltonian. And we can also use it for a few particular calculations. In particular, we can calculate numbers like the string breaking energy, the potential between adjoint quarks, etc., and compare with experimental lattice data, and it seems to work reasonably well. So this is the bit that I had in mind to tell you about as far as the problem of adding coupling matter fields to Yang-Mills theory in 3 dimension is concerned. And what I'd like to describe to you briefly next is yet another avenue in which we are trying to push the framework of KKN. And that has to do with studying Yang-Mills theories with or without matter fields on spaces where the spatial geometry is compact. So so there are many motivations for doing that. As I mentioned briefly before, there is a concrete string proposal for what the spectrum of the supersymmetric version of the gauge theory will look like on R cross S2. So adding matter fields and having supersymmetry is not really a problem because that we have figured out. But getting non-trivial, describing gauge theories on non-trivial spatial geometries is a bit of a technical problem. And the technical problem has to do with the matrix parameterization, which was so useful in the original work of KKN. So let me just describe for you briefly the kind of problems that one might potentially face. So remember, for the case of the plane, it was very useful to think of the plane as a complex plane. So if we were to look at the sphere, for example, we should naturally think of the sphere as CP1, which is SU2 mod U1. And that basically tells us that we should work with the good old-fashioned stereographic coordinates. So we have this complex metric on the sphere. And the role of del and del bar are now played by the raising and lowering operators for the SU2, R plus minus. One can try and repeat the same story for the gauge, for the old story of the matrix parameterization, but that one has to do with a little more care, because on the plane, this operator del had no zero mode. So this was modulo this holomorphic symmetry. This was a one-to-one parameterization. However, on the sphere, the R plus operator does have a zero mode. So ostensibly, at least, there is a bit of a problem. So remember that this, for example, this object came about in various formulae for the Hamiltonian, various formulae that I've been using describing the Hamiltonian. It's just the Green's function for the Dirac operator. And the fact that it's a Green's function was key to many of the calculations that we did, for example, the estimates of the bound state energies and so on. But of course, that wouldn't be the case if we had the sphere. There'll be a contribution from the zero modes, etc. So on the face of it, at least, it looks like there's a bit of a technical problem. The good news is that one can subtract out the zero modes by hand, and it's really a bit of an illusion. It shows up at various intermediate stages of the computation, but at the end of the day, everything that one could do on the plane, one can do for the sphere also. So one can write down the Hamiltonian, the kinetic and the potential energy terms in terms of the gauge invariant variables, just like one had before. And one can even compute the vacuum wave functional as an expansion in 1 over m, etc., like one did before. So this is, again, the leading order piece. So if we now just look at the leading order piece and write everything in terms of dimensionless objects, then we get basically two-dimensional Yang-Mills theory once again, where the two-dimensional dimensionless coupling is given by the square of the mass gap times the area of the sphere. And this is really the leading order piece in the vacuum wave functional. But of course, this is a very interesting quantity, because we know that 2D Yang-Mills theories on the sphere, unlike the plane, undergo a strong weak phase transition, the so-called Douglas-Kazakov transition. So one could ask that if indeed we trust this formula for the wave functional, because this was a very trustworthy formula for the plane, then does that really mean that there is a phase transition for the gauge theory on the sphere at zero temperature? So that is, of course, an interesting possibility that is pointed out. And indeed, if one just looks at the weakly coupled gauge theory at finite temperatures, which was analyzed by Ramstonk and collaborators some time ago, what they find is that there is indeed a Douglas-Kazakov transition for the three-dimensional gauge theory on a sphere on top of the usual Hagedorn deconfining transition at high temperatures. So what they did was, what they find is the Douglas-Kazakov transition at weak coupling, high temperatures, what we seem to be saying is that if we really trust this formula for the vacuum wave functional, and we have reasons to do so from our experience for the planar case, then it looks like there's a phase transition for the gauge theory now at strong coupling but at 0 temperature. But we have to be a little more careful and interpret this carefully. So the Douglas-Kazakov transition really takes place when the dimensionless coupling of the 2D theory is less than a particular number. This is the sort of weak coupling phase of the theory. So can we really reconcile this with the fact that we have this as a description of the strong coupling phase of the gauge theory? Well, once again, we have to ask the question what we really mean by strong coupling. So for example, if one were to look at the full kernel that has all the momentum-dependent corrections, then we would say that this wave functional is really describing the theory, is to be thought of as describing the vacuum of the theory for all momentum modes less than the dimensionless coupling. What the Douglas-Kazakov transition tells us is that the inequality tells us is that it places a number for those momentum modes. So what it is saying is that if this is really a good description of the vacuum for the wave functional for all momentum modes less than a particular number, then indeed it looks like there is a phase transition at 0 temperature but at weak coupling. That wouldn't be surprising, once again, given the fact that the transition exists at weak coupling but at high temperatures. But of course, this is a statement that will be true only if we have we believe this wave functional to be accurately describing the theory for all momentum modes down to this number. Of course, that is a possibility that is pointed out, but it would be very interesting, for example, to see if the momentum-dependent corrections do change the structure of the phase transition and so on. And that is a problem that we are analyzing. But
What kind of phase transition is it supposed to be? What's the order parameter?
the Douglas-Kazakov transition?
I mean, in this three-dimensional context, what would it
Okay, so if you just looked at the Wilson loop averages, for example,
Yes.
it's once you have this, it's a 2D problem now. Once you have the the formula for the vacuum wave functional. So in the 2D setup, you look at a Wilson loop expectation value, and when you go to this regime, you see that there is no area law.
So it's sort of deconfinement for the spatial Wilson loop of the three-dimensional theory, but
Yeah.
perhaps not for the Polyakov loop.
No, not the Polyakov loop. It's the spatial Wilson loop of the theory. So, right. So there is this interesting possibility that basically we get for free once we try and attack the problem on the sphere. So of course, a lot needs to be done, and so as I pointed out, one thing that we are doing is analyzing the theory on the sphere in greater detail, understand the nature of the phase transition and so on. And the other aspect that we are trying to work out, now that we understand how to couple matter fields, how to write the theory in non-trivial spatial geometries, etc., what we would really like to do is analyze supersymmetric gauge theories as strong coupling within this formalism, especially the theory related to LLM geometries, which is n equals 4 superangles on R plus S2, and it looks like one can do actual calculations and come up with numbers and so on. So a lot needs to be done, but I guess I've convinced you that there's at least some reason to be optimistic. So with that, let me stop.
Yeah, L times L plus 1 less than pi squared does not look particularly promising.
Sorry?
L times L plus 1 less than pi squared doesn't look particularly promising. You might get L equals 0, L equal 1, and maybe L equal 2, but
Right. So the thing is that is this wave function really accurately describing the gauge theory down to the lowest L equals 1 mode? And I mean from the experience on the plane, it looks like it's a very accurate description. But of course, so there are two aspects to it. I mean, to really answer your question in sort of a technical sense, there are two aspects to it. So there are two kinds of corrections to the wave functional. One are things that depend only on traces of B, traces of powers of B. These would sort of give you a generalized 2D Yang-Mills, and that we know doesn't change the nature of the phase transition. that still gives you a Douglas-Kosakov transition. The real technical question is, do the momentum-dependent contributions change the nature of the phase transition? And that we don't know quite yet, and that's a problem we're analyzing. The thing is that the moment you have these momentum-dependent contributions, it's not so easy to apply the usual tricks of 2D Yang-Mills theory and reduce the problem, use the invariance until you're preserving diffeomorphisms and so on. So it becomes a bit harder, but the real question is, do these momentum-dependent transitions change anything? So unless we figure that out, it's really hard to say for sure that there is a phase transition. The possibility is pointed out, but we're trying to see what the momentum-dependent guys do.
Anyone?
Okay, let's thank Abhishek again.